So sometimes a molecule can be represented by multiple valid Lewis structures that differ only in the placement of electrons. This is called resonance. So let's say you're given the compound NO3 minus, a nitrate ion, and then you want to show resonance for this compound. So what you would want to do first is to draw out the Lewis structure. And so far with the knowledge that the video provided, um, it should be quite difficult to draw the Lewis structure, but I'm going to go ahead and walk you through it and explain why it is the way it is. So first, we're going to draw the single bonds to the 3 oxygens, and then before that, you should probably count the number of electrons we have. So we have 1 nitrogen, that's 5, 3 oxygens, that's 18, and then 1 more because of the negative sign. That gives us a total of 24. So start off by giving the 2 oxygen on the right and left, 4, and then this one as well, 4, right? And then now we have 2, 4, 6, 8, 10, 12, 14, 16, 18, and so now we have 6 left. So next, you're going to want to put 2 more on this oxygen, and then 2 more on this oxygen as well. And now, the reason for this is the only way that the resonance structure would work in terms of the positioning of the electrons. And so um, let's calculate the formal charge for these oxygens. So I'm going to go ahead and put the negative charge there. And so we know oxygen has 6 valence electrons, right? Minus the number of non-bonding electrons, minus 1/2 the bonding electrons, which is 2, right? So now 6 minus 6 is 0, minus 1 is equal to negative 1. So that's the charge for these two right here. And now, like I said, we have only 2 more left, 2 more electrons left, and we're gonna draw a double bond here, right, from the nitrogen to the oxygen. And so if we were to just give the oxygen the other 2 electrons, it would be negative, right? And so you'd have a triple negative, and then you'd have a double positive charge on the nitrogen, and that would make the compound very unstable. So that's why we have to draw the double bond here. And so right now, let's calculate the formal charge for nitrogen. So nitrogen has 5 valence electrons minus number of non-bonding electrons. Right here, we can see it doesn't have any. So 0 minus 1/2 times 8, which is the bonding electrons, 2, 4, 6, 8. And 5 minus 4 is just going to equal to positive 1. So here we have a plus 1 charge. And then the total charge is just going to be a negative 1 charge for the compound. Now, let's draw the resonance for this compound, and I'll explain why it is the way it is. So, go ahead. So we have this double-sided arrow here represents resonance. And so to show resonance, resonance is just the movement of electrons. So you're not moving the atoms around at all. And in this case, the resonance is achieved by moving these electrons right here on the double bond, and then we could either choose this oxygen or this oxygen, and then forming the double bond here. And then there we have it. We have one of the resonance structures for the nitrate ion. So now the double bond here, right? And now this oxygen is negatively charged. Okay. And then now we have the other resonance structure, which I'll just show like here. And so the way I'm going to show this resonance structure is put this back here, and then these two, take them right here. And so what we end up with, so with resonance, you're just looking for any way you can move electrons around that doesn't change the orientation of the compounds and only changes which compounds have which charge. And then that gives you major contributors for resonance structures. So here, and then this one right here. And those are the resonance structures for the nitrate ion, NO3 minus. And so this is a bit of a difficult example, but I plan to have a video where going through other examples that are like more simpler and then build up and eventually get more and more difficult, and just for practice. So now let's go ahead and try a different example. So here I have this compound. So for this carbon right here, go ahead and pause the video and try and figure out the hybridization on your own. So this example requires some knowledge about carbon skeletal structures, and so I won't go into much detail about that in this video, but if you'd like to see a video, let me know explaining skeletal structures in more detail. So here we see that their carbon has no lone pairs, and it's bonded to a hydrogen here, to this ethyl group, and then it's in a membered ring, 6-membered ring, and it's bonded this way and that way. So it has a total of 4 bonds, making it sp3. So now instead, let's say you have it like this. Determine the hybridization of the carbon now with the double bond. So here we see that it's bonded here once, 2, and then 3 to this carbon. So double bonds count as it contribute only 1 to the hybridization, and so triple bonds as well only once, and single bonds as well, of course. And so this would make this bonded to 3 atoms, making it sp2 hybridized. So now instead, let's say we have a triple bond. What would be the hybridization now? So this carbon now, it's bonded here and it's bonded here. So the triple bond contributes only once to the hybridization, and the single bond contributes once, and so it has a total of 2 atoms that it's bonded to, making it sp hybridized. Let's move on to a different example. So let's say we have this compound, ethylene, C2H4. If we were to draw out the structure, it would look like this. So carbon to carbon double bond, and then 2 hydrogens for each carbon. So in this case, carbon mixes 1s, 1 2s, and 2 2p orbitals, leaving 1 2p orbital from each carbon unhybridized. The 3 sp2 orbitals line a plane forming sigma bonds with hydrogen and the other carbon. So 1, 2, 3 sp2 orbitals, right? And the leftover unhybridized 2p orbitals overlap side by side to form a pi bond, which is the second bond seen here, and that causes the double bond. And the pi bond with the other sigma bond makes up the CC double bond here. And because pi bonds require side-by-side overlap, rotation around a double bond is restricted, and turning it would break the pi bond. And so if you have a molecular model kit, you could try and do this on your own and try twisting it and see what happens. Probably be kind of difficult and it might break, so be careful. But next, let's move on to an example of sp hybridization. So let's say we have C2H2 acetylene. So now you have a carbon and another carbon, right? And so in this case, it's going to be a triple bond between them, and then they're bonded to an H each. And so let me redraw that. And so this sp hybridized compound, acetylene, the carbons mix one s and one p orbital, leaving two unhybridized p orbitals from each carbon. And those unhybridized orbitals form two perpendicular pi bonds, seen here. And this produces the CC triple bond, along with the sigma bond from between the carbons. And so you have a sigma bond, and then you have two pi bonds between them, forming the triple bond. So what we get from this is that as the number of bonds increase, the atoms are pulled together, leading to shorter, stronger bonds. So this is just a general rule. As you increase in S character, the bonds become shorter and thus stronger because the atoms are pulled together. And so just in terms of a single, double bond, and triple bond, just think of this as being shorter than this one, and this one shorter than this one. And so a single bond is the weakest, then you have double bond, and then you have the triple bond being the strongest. So next, let's move on to hybridization. And so hybridization is a molecular orbital theory that explains how atomic orbitals combine to form equivalent bonds and molecular shapes. So let's start with methane. So if you look at the carbon in methane, right, and look at its ground state electron configuration, you're going to have 1s2, 2s2, and 2p2, right? And so that means two paired electrons in 2s and two unpaired electrons in 2p, which is not enough to make four identical bonds. So to form four equivalent bonds, carbon hybridizes one 2s orbital with three 2p orbitals, and this produces four equivalent sp3 hybrid orbitals. Right? So each sp3 orbital overlaps with the 1s orbital of hydrogen, forming four identical sigma bonds. And this pretty much allows for carbon to be arranged in a methane to be arranged in a tetrahedral shape with the bond angles at 109.5 degrees, which provides maximum separation between bonds and minimal electron repulsion. So this is how it would look like. So that's going to be it for this video, but in the next video, if you'd like to see me explain carbon skeletal structures, please let me know, because that is a concept that's, I would say, required in organic chemistry, just knowing the formula from the carbon skeletal structure. So if you'd like to see that, please let me know, and thank you for watching.